Good morning, everyone. My name is Indira with the student ID number of 24055318080. In this video, I will be presenting based on the book Manufacturing, Engineering, and Technology, 6th edition, more specifically in Chapter 2, which is Mechanical Behavior, Testing, and Manufacturing Properties of Materials. Before we dive into the test and formulas, let's begin with an overview of what Chapter 2 is really about. This chapter is focused on the mechanical behavior of materials, which means how materials respond when we apply forces to them. Every manufactured product, from cars and airplanes to phones and bridges, relies on choosing the right materials that can withstand the loads it will face during its service life. The key idea is that different materials behave differently under loading. Some are strong but brittle, others are ductile but weak, and some can deform a lot without breaking. To design safely and efficiently, engineers must measure and understand these behavior. Now, let's move on to the first test, which is tension testing. The tensile test or tension test is the most widely used mechanical test because it gives us nearly all the fundamental mechanical properties of a material. In this test, a specimen, usually shaped like a dog bone, is gripped at both ends and pulled in tension until it fractures. The tensile machine records the applied load and elongation, from which we calculate stress and strain. Stress is the internal force per unit area inside a material when an external load is applied, and strain is the measurement of deformation, how much a material stretches or compresses relative to its original length. In here, you can see that figure 2.2 is a typical stress strain curve obtained from a tension test. So this is an example of a stress strain curve itself. So the resulting stress strain curve reveals several regions. The first one being the elastic region. Here, deformation is reversible. Stress and strain are proportional, and the slope gives us Young modulus, which represents stiffness. The second one is the yield point. Beyond this point, deformation becomes permanent. The material won't return to its original shape even if the load is removed. The third is strain hardening. As the specimen stretches further, dislocation interact and make the material stronger, so more stress is needed to continue deforming it. The fourth, it begins to neck or necking. It is the after the maximum stress is reached, the ultimate tensile strength, the specimen begins to thin locally. This reduces its load carry ability. And the last, fracture, where the specimen itself breaks. Figure 2.4 is the approximate relationship between elongation tensile reduction of areas for various groups of metals. Moving on to the next slide. Here I put all the formulas needed to find the stress strain curve itself. There is stress engineering, strain engineering, true stress, true strain, elastic modulus, and toughness. So for example, if you were to find the stress, it is sigma per applied force. It is sigma equals to applied force per original cross-sectional area. And if you were to find the strain, it is the epsilon or strain equals to delta L or the change in length per original length. Next, we move on to compression test. While tension testing are most common, manufacturing processes such as forging, extrusion, and rolling actually apply compressive forces. In the compression test, the specimen is placed between two platens and they are squeezed. The stress is calculated the same way as in tension, but the sign is opposite, compressive instead of tensile. The two main effects are observed, which is barreling, where the specimen bulges outward in the middle because of friction between the platens and the specimen ends, and buckling, for slender specimen. Instead of shortening uniformly, the sample may bend sideways when the compressive load exceeds a critical value. Compression testing is critical for determining compressive yield strength and flow stress, values that are essential for simulating the formation process. This figure right here is an example that shows the direction of loading and the fracture path. Next, we move on to torsion test. In a torsion test, instead of pulling or pushing, we apply torque to twist a specimen. Tubular specimens are often used to avoid stress concertation in the center. Torsion test gives us properties such as shear modulus, or G, shear strength, and ductile in shear, all very important for shafts, axles, and rotating machinery. This test is important because many engineers' failures involve torsion. Measuring how materials behave in twisting ensures reliable designs for power transmission components. 2.5 is about bending or flexure test. Bending tests are especially used for brittle materials like ceramics, glasses, and some composites, because these materials fracture suddenly in tension and are difficult to test in a standard tensile setup. In a three-point bending test, the specimen is supported at both ends and loaded in the middle. In a four-point bending test, load is applied at 2 points, creating a region of uniform stress between them. In here, there is also the formula for stress sigma and strain epsilon. This is an example itself of the bending or flexure test. Now, let's move on to hardness. Hardness is the resistance of a material to permanent deformation, usually measured as resistance to indentation, penetration, or scratching. It is not a fundamental property like stress or strain, but it is extremely useful because it correlates well with strength, wear resistance, and the ability of a material to plastically deform. Several different hardness tests exist, each with its own advantages. So the first one we're going to be talking about is the Brinell hardness test, or BHN. BHN uses a hardened steel or tungsten carbide ball pressed into the surface under a known load. The size of the indentation is measured and the hardness is calculated. For example, BHN equals to 2 applied load per P ball diameter and diameter indentation diameter. Next, there is the Rockwell hardness test, HR. The Rockwell hardness test is faster and more widely used. It measures the depth of penetration under a minor and major load. The result is given as a number with a scale, such as HRB or HRC, depending on the indenter and load. This method is excellent for production testing. Next, we have Vickers and Knoop, or micro hardness. For very small or thin materials, we use micro hardness test. The Vickers hardness number, VHN, for instance, is based on the load divided by the surface area of the indentation, using a diamond-shaped indenter. The formula is as shown as below. Finally, the Mohs scale. It is the simplest. It measures hardness based on scratch resistance. It ranks materials from 1 top to 10, which is diamond. These are the selected hardness testers. Hardness is especially important in manufacturing because it often gives a quick estimate of material strength and wear resistance. That's why hardness tests are used extensively for quality control in the industry. Shown in the slide is the general characteristic of hardness testing methods and formula for calculating hardness. Next, let's discuss fatigue, which is one of the most important failure mechanisms in engineering. Fatigue is the progressive failure of a material under repeated or fluctuating stresses. The critical point is that fatigue failures occurs at stress levels much lower than the material's static tensile strength. This is why fatigue is such a dangerous and common failure mode. It accounts for the majority of mechanical failure in services. Fatigue occurs in three stages. The first is crack indentation, usually at the surface or at a defect such as a notch or a scratch. The second is crack propagation, where the crack slowly grows with each loading cycle. And third, the final fracture, which is often sudden and catastrophic once the crack reaches a critical size. The behavior of materials in fatigue is typically represented by the S-N curve, where stress amplitude S is plotted against the number of cycles to failure N. For many steels, there is an endurance limit, a stress level below which the material can theoretically endure an infinite number of cycles without failing. The relationship between stress amplitude and cycles to failure is often expressed using Baskin's law. Creep is another long-term failure mechanism, but it is different from fatigue. Creep is the slow, time-dependent deformation of a material under a constant load, and it becomes significant at high temperatures, typically about zero point 0.4 of the material's melting temperature in Kelvin. The typical creep curve has three distinct stages. The primary creep, where the creep rate decreases with the time because of strain hardening. Secondary creep, where the material reaches a steady state creep rate, often considered the most important stage for a design. And the third, tertiary creep, where the rate accelerates rapidly, usually due to microstructural damages such as grain boundary voids leading to rupture. The steady state creep rate can be modeled by the following equation that you guys see on the screen right here. Now, let's look at impact testing. Impact test measures the ability of a material to absorb energy during sudden dynamic loading. Unlike the tension or compression test, which applies load gradually, impact tests simulate real-life situations like a hammer strike, a collision, or a falling object. The two most common methods are the Charpy test and the ISA test. In the Charpy test, a notch specimen is supported horizontally like a beam and struck in the center by a swinging pendulum. In the ISO test, the specimen is clamped vertically and the pendulum strikes near the top. The machine measures the loss in potential energy of the pendulum before and after striking, which tells us how much energy the specimen absorbed before a fracture. One of the most important results from impacting testing is the ductile to brittle transition temperature, or DBTT. Many steels, for example, are ductile and tough at room temperature, but become brittle at low temperatures. This transition explains catastrophic failures in structures like ship, pipelines, and bridges in cold environments. This test is important because impact testing gives us a measure of toughness under dynamic loading, which is essential in industries like automotive, aerospace, and construction where materials often face shock or sudden loads. Next, let's consider failure and fracture. Fracture toughness is extremely important in designing critical components such as aircraft fuselages, pressure vessels, and nuclear reactors. Even a small crack can grow under stress and lead to catastrophic failure if not properly accounted for. Materials can fail in two distinctive ways. The first is ductile fracture, where the material undergoes significant plastic deformation before breaking. The fracture surface is rough and has a characteristic cup and cone appearance. Ductile fracture absorbs a lot of energy, which makes it safer because it usually provides visible warning before failure. And the second one, which is brittle fracture, where it occurs suddenly with little or no plastic deformation. The fracture surface is flat and shiny, often perpendicular to the applied stress. This type of failure is dangerous because it happens without warning and with very little absorbed energy. Residual stresses are internal stresses that remain inside a material even after the external force have been removed. They often result from manufacturing process such as plastic deformation, machining, welding, or heat treatment. These stresses are locked in at the microscopic or macroscopic level. Residual stresses can be beneficial, such as compressive residual stress at the surface introduced by process like shot peening or surface rolling. These improve fatigue resistance because they suppress crack penetration and growth, or they could also be harmful, such as tensile residual stresses at the surface, which promote cracking, wrapping, or premature failure. Welding, for example, often introduces such stress if not controlled. Engineers often use stress-relieved heat treatment or mechanical methods to reduce unwanted residual stresses. So here, as we can see on the screen, figure 2.3 is the distortion of parts with residual stresses after cutting or slitting. Finally, let's talk about the connection between work, heat, and temperature during plastic deformation. When a material undergoes plastic deformation, the mechanical work done on the specimen is converted into heat. This causes a temperature rise, especially if the deformation occurs rapidly. In processes like forging, extrusion, or rolling, much of the mechanical energy is dissipated as heat. In fact, about 90 to 95% of the plastic work is converted into heat, while only a small fraction is stored in the material as defects, like dislocations. This temperature rise can significantly influence the material's behavior. At high strain rates, the materials may soften locally due to adiabatic heating, leading to localized deformation called shear bands. In hot working processes, such as hot rolling or forging, the heat helps keep the material soft and ductile. Whereas in cold working, the lack of significant heat dissipation makes the material strain harden, which increases strength but reduces ductility. That is all that I have to offer in this video. I deeply apologize if I said any grammar or pronunciation, if I mistake anything, or if I give you the wrong idea. Nonetheless, thank you so much for listening, and see you next time.